Hello, I hope you all well. Welcome back to another lecture. In this lecture, I want to talk about dead load and how we're going to calculate dead loads. Let's look at the definition of dead load based on ASCE 7. And that is basically everything is dead that is not moving, which consists of the weight of the material. And that can be included but not limited to the wall, floor, roofs, ceiling, stairway, furniture, whatever you have in a room that is not moving, it basically can be considered as a dead load. And one of the things I'd like to also continue before we start, a few rule here, and that is the term of load and forces are often used in here, and they both really are the same thing. And in the English system, we're going to use pound and kips, and of course in the SI system, we're going to use Newton and kilonewton. And also we talked about turbatory area, which is each load on a structure is supported entirely by the nearest structural member. And we're going to go ahead and when we do these load calculation, we're going to use the minimum design load for building and other structure, which could be based on ASCE or Building International Code, or it could be AASHTO, or it could be any of those you see on the board here. All right. So before let's start out with an example how we're gonna do this. We want to calculate the dead load on this beam right here, beam B right here, and this beam right here. They're both the same type of beam, and it's supported by this girder right here, and of course, an in turn is supported by this column, and this whole bay is covered by a 5-inch concrete slab right there. So let's go ahead and figure out. We're going to put this into 2D dimension. And okay, now you saw the 3D on a rivet. So let's look at the plan view of it. And this is the same, these girder B2 on outside is supported by the column. And the inside beam are supported by this girder B1. And the beam are about 8 feet apart. What else? And the connection between the beam and the girder is a pin connection, so it doesn't carry moment, transfer moment. And when we look at the cross section, take cross section here, we're going to see the concrete slab is about 5 inch on top of the beam, and then you have the ceiling and all their stuff. And the ceiling itself is a 1.5 pound per square foot. And then watch for your unit. And then all the stuff inside here, the ducting and all the pipe, let's say that comes out to 20 pounds per square foot. You usually find these in a code, and they tell you what to use. And based on experience, a lot of designers can tell you all that stuff. So now we have this stuff. Our goal is to find out how much load is on this beam B1. All right, and if you look at it and we go ahead and draw it, do a free body diagram, and this is the load I'm looking for, the uniform load on top of this beam, and then what's going to do on a girder itself when it's supported by the girder. We talked about in the previous lecture turbatory area. Before I go ahead, I got to find out what's the turbatory area of this beam. So I got to go halfway from here, or halfway between here and that beam. So it's halfway between here and there. It's going to be like 4 feet. That's a nice line straight drawn. And that's another 4 feet right there. So this distance, basically, it's going to be 4 feet and 4 feet. And that's inside of the pink area. It's my turbatory area for the beam B1. And now we have that. We have our load. So let's calculate these load on top of it. Calculate the uniform distributed load on this B1, which is supported by a girder at girder of B2 on both sides, those point 1 and 2. So point 1 and 2 is supported by these two girders. And now we are gonna go ahead, and the first thing we're gonna use, we gotta find out the turbatory area, which we talked about this here. Let's use the concrete slab first, and that's 150 pound concrete per cubic feet. Okay, multiply by 5 inches, which divide by 12, and then we're going to multiply by 8, which is very important. 8 is the width of our turbatory area, and that should give me 500 pound per foot. All right, next thing we're going to find out, let's find the weight of the beam itself, which was given to us. So this is the weight of the concrete, and weight of the beam, it was given as 30 pound per foot. And then let's go a little bit lower, find the weight of the duct and all the stuff, and that's given at 20 pound per foot. Okay, weight of the duct, and that was 20 pound per square foot. Remember your unit here. Multiplied by the turbatory width, and that's 8 feet, and that should give me 160 pound per foot. The next one I have is weight of the ceiling. I think that's how you spell it. How much was that? 1.5. 1.5 pound per foot. Multiply that by 8, give you 12 pound per foot. So the total load weight of the dead load that we have, it's going to come out to 702 pound per foot. Let's call it 0.7 kip, or 0.71 I have up there. Okay, so 0.71 kip, that's going to be right here, and the reaction force we're going to calculate, it's going to come out to 0.875. Then that was the beam B1. Now let's take a look at the girder B2. And we take a look at girder B2, we have this weight right here, that's weight of the girder itself, which is 0.05 kip per foot, which is 50 pound per foot. That's assumed that, and we assume the weight of the beam is 30 pound per foot. And then you have these two reaction forces, which we have found right here, and those are 8.75. Then you can find this reaction yourself. You can do that on your own. I think I have the answer, and you can double check my answer. It comes out to 9.475, and that's easy. If you forgot how you did that, you take a moment about this point, and you have this to concentrated load. You convert your uniform load to a concentrated load right here, which is the 0.05 times 24, and bang, you can have that answer. So that's it for dead load calculation, and be well until next time we're going to do life load.